Hello and welcome to the sample lecture, Croeso I darlith sample. I'm Dr. John McRory and today I'm going to be your guide through the wonderful world of dynamics. Now, as you're aware, we've had to move things online, so thank you for joining me here in my kitchen conservatory. But it does mean that this sample lecture is going to be slightly different to a regular lecture. There's normally more back and forth discussion or questions from both myself and members of the audience, and all of that helps keep energy in the room. But in the absence of that, I'm going to do my best to try and hold your attention whilst giving you an insight into how lectures could be delivered at university. Now, the first thing we normally do when we start a new lecture series is we give some context for the material that's about to be covered. So we look at real-world examples. We also talk about the vocabulary of terms that might be specific to that material and outline the learning objectives that the student's meant to pick up over the course of the module. And if I apply the same sort of approach to this sample lecture, as I alluded to at the beginning, we're going to be looking at dynamics, which is the study of motion and moving things. It's also the subject which I lecture on, so obviously it's the best one. Now, I'm not going to have that long with you today, so we're not going to have a long list of learning outcomes, and we're not even get that too deep into the content itself. But I do hope you walk away from this with not only a better understanding of how education can be delivered at university, but also of dynamics itself. And I'm hoping that we start to probe some of the simplifying assumptions that you might have been making in your own studies so far, which you may or may not even be aware of. So more on that later. So, why study dynamics, I imagine hearing you ask? Well, once you've mastered the dynamics toolkit, you can analyse moving systems. You can calculate how one part of a mechanism might move relative to another. And further to that, you could even design your own mechanism which moves in a very particular way which satisfies a need. And after all, that's a lot of what engineering is about. We apply maths and physics to come up with solutions to real-world problems. So what kind of mechanisms am I talking about? Well, essentially anything that moves, so there's quite a lot of examples. But it could be something mundane, like a handheld electronic fan. That's going to have some batteries which apply power to a motor. The motor supplies a torque which accelerates the propeller. Hey presto. It's quite simple to break down. If we increase the scale of that quite a lot and increase the complexity in doing so, we end up with a wind turbine. Now, this is kind of the same affair, except in reverse, because this time the rotation of the blades turns the generator, which is producing electricity. It's not just rotating systems. We also have things which have maybe rotating links with sliding motion, such as in this hand press here. So with this, you've only got a few rigid bodies moving, but that's what makes it such an ingenious solution, which allows you to apply more pressure than you otherwise would be able to by hand. And if we come on to something that I think is the pinnacle of dynamic study, it would be robotics. And the work they've done over at Boston Dynamics is truly incredible, if a little terrifying. I heard recently actually that they were going to release robotic dogs into parks to disperse crowds, which, yeah, it's amazing. But also, I feel like that's how Skynet starts, so not entirely sure how I feel about that. But yeah, so to break down just slightly what makes this robot so incredible is that in real time it's having to be aware of the position of all its limbs and parts in 3D space. Combine that information with the information about the mass of each part to work out its centre of gravity, and then provide enough force and torque to all its actuators I should say, to keep itself upright, all whilst executing the desired command, like walking or jumping. And like I say, it's doing that real time, so it's having to update itself every fraction of a second. It's effectively doing what you or I do when we walk and we maintain balance, but we do that subconsciously. Programming something and designing something that can do that deliberately is a huge challenge. So that's pretty amazing. But even if that's, say, maybe one of the end goals, we have to bring it back at the start of our studies to slightly more humble beginnings. Now, if we were in the same room at this point, I'd probably have started to see some eyes glaze over. And that's because I slipped into using course-specific vocabulary. Obviously, quite a difficult thing to avoid whilst I'm talking about the course. But that's precisely why in the first few lectures we start to introduce the new vocabulary and sort of talk about what it means in an engineering context, because particular words and particular phrases sometimes take on very specific meanings. For instance, in the context of dynamics, when I said a rigid body, I don't just mean that it's quite hard. When I say rigid, I actually mean that it cannot deform at all under any applied loads and moments. Now, obviously, that's a simplifying assumption because real bodies would deform under loads and moments. But by making that simplifying assumption in the first couple of years when we start to look at dynamics for the first time, it means that you can be concentrated on the geometry of motion itself and not have to worry about how the bodies might be changing shape during that process, which would then change all of your calculations and make it a lot more complicated. Also, you could even throw the word body under the microscope. I mean, a body is something which has a finite size, i.e. it's not an infinitely small particle. Now, an infinitely small particle can move around in 3D space. It can go up, down, left, right, forwards, back, but it can't rotate, because there's nothing for it to rotate about, it's infinitely small. A body, on the other hand, which has a finite size, can move around in 3D space, but it can also rotate, because it has a physical size. And whilst this sounds like such a mundane observation to make, the simplicity is deceptive, because this whole business of rotation can cause you a headache if you don't approach it in the right way. Now, dynamics can be thought of in two main sections. There's kinematics, which is the study of the geometry of motion, and kinetics, which is the study of the forces which underpin motion. And you might have come across these two things already. For instance, let's take this example. If we have a box and we put it on a surface, so let's say that box has a mass of m, and we try and push the box with a force which we'll call P. Now, due to the interaction between the box and the surface, there might be some frictional resistance to this force. But if we take the resultant, if we take the sum of those forces, it will be equal to the mass of the box multiplied by the acceleration. So now we're talking about Newton's second law, F equals ma. This is an example of kinetics, because it's looking at the forces which underpin motion. Now, when we treat the box this way, you may or not be aware, but this is a simplified assumption. We're actually treating that box as a point mass, because we're not considering its ability to rotate. If we do instead look at a body where we're considering the rotation, so let's take this link, and if we pin the link at the bottom, it's obviously going to rotate about that point. Now, I guess you could think of this in the kind of context of one of those gates that you get at the entrance or exits to car park. Not a particularly glamorous example, I know, but we have to start somewhere. So if I apply the same kind of force, P, to the top of this link here, how would I use my F equals ma equation to work out the acceleration of the link? Would I say that the acceleration of the top point near where the force is applied equals the sum of the forces divided by the mass? Or would I say that the acceleration of the centre of gravity of the link, somewhere near the middle, equals the sum of the forces divided by the mass? Well, the short answer here is that F equals ma is not going to give us any satisfactory solutions, because that acceleration value it's looking at is a translational acceleration, like a linear acceleration, not a rotational one. And if this were a real lecture now, at this point, we'd have to go back to first principles and derive new equations of motion that allow us to deal with rotation. Now, I'm not going to do that here because it would take the best part of an hour and it sort of falls outside the scope of what we're trying to achieve with the sample lecture. But if I jump all the way to the end of that process, we essentially end up with a new equation. And that's that the sum of the moments equals the inertia of the body multiplied by its angular acceleration. Now, hopefully you can see that there's quite a lot of similarities between this and the equation we were just dealing with, because instead of the sum of the forces, we have the sum of the moments. But moments are essentially just rotational forces. And instead of the acceleration, the translational acceleration of the body, we have this alpha, which is the angular acceleration to do with rotation instead. So now we have two equations, one which deals with translation and one which deals with rotation. And that is like another it's another item in our engineering toolkit, which allows us to tackle new and different problems. So if we go back to thinking about this thing as one of those gates, we'd now be able to specify and calculate how much torque we'd need to apply in order to rotate and lift that gate against its own mass. And if we increase the complexity slightly, let's say we add another link to the end of this, you can hopefully already start to see how the same kind of analysis process could be used to calculate the movement or even design a simple robot arm mechanism. And even if this mechanism is simple, it still has a plethora of uses in things like manufacturing, experimental science, medical science, or desktop working where you have human-robot interaction and collaboration. So I just checked the time and we're coming up to the limit for this session. So I hope that you've enjoyed it. And I hope you found it useful to see the kinds of discussions that happen at university and how lectures could be delivered, and also that I've helped sow the seeds of curiosity. I guess another takeaway from this is that a university education should take your understanding from a level where you can calculate specific features of a restricted system to the point where you could design bespoke solutions for real-world problems. So yeah, I hope you enjoy the rest of the virtual open day and maybe see you in the next academic year. Who knows? Thank you very much. Diolch yn fawr.